Welcome to Tech Explained. Today we're embarking on an in-depth exploration of CISSP Domain 6, Security Assessment and Testing.
That's right.
This area isn't just a chapter in a textbook, it's really the very heartbeat of ensuring an organization's security posture is genuinely effective, robust, and resilient.
Yeah, the whole life cycle.
What's the central challenge we're trying to solve here? How do we really know our security works, beyond just hoping?
That's precisely the challenge we're tackling. Think of this domain as the ultimate validation step for every single security control an organization puts into place.
Okay, validation.
Yeah, it's simply not enough to implement sophisticated firewalls, encryption, or access controls, and then just assume they're doing their job.
Right, assumption isn't security.
Exactly. You need to constantly, rigorously assess and test them to ensure they're performing exactly as intended and, crucially, that they're actively contributing to the organization's overarching business objectives.
Business objectives, that's key.
Absolutely. It's about building tangible confidence in your security posture, demonstrating that the significant investments in security are truly delivering measurable results and protecting what matters most. Without this validation, security is just, well, a series of assumptions.
So let's really get into the core purpose then, security assessment and testing within an organization. What is the fundamental aim here when we talk about providing assurance?
The primary focus really is on providing undeniable assurance to stakeholders, from the C-suite down to individual users.
They're involved.
Exactly. This isn't just about ticking boxes. It's about demonstrating unequivocally that security is effectively contributing to the organization's objectives. This translates to ensuring that the right level of security is embedded into every architecture, every system, and every process from the ground up. Not as an afterthought. It's a continuous effort to validate that security requirements aren't just defined on paper during the planning phase, but that they are properly tested, operating effectively, and remain relevant throughout an asset's entire lifecycle.
The whole life cycle again.
Yeah, this includes brand new applications as they're developed, ongoing operations for existing critical systems, and even during their end-of-life phases. Security decommissioning is paramount there.
To prevent data leakage, right?
Exactly. Data leakage or unauthorized access. Ultimately, it covers both the functional aspects, what a security control does in practice, and perhaps more importantly, the assurance aspect.
Which is?
The verifiable proof that it actually works as intended and delivers the expected protected benefits.
That distinction between functional and assurance is key. And speaking of ensuring things are right, we often hear two terms that sound very similar but have critical differences: validation and verification. Could you help us understand the nuances between them?
Absolutely.
Yeah.
Let's start with validation. This process actually begins before an application or product is even built, right at the requirements gathering stage.
Before development start.
Yes. It's about asking the fundamental question: are we building the right product in the first place?
Okay, the right thing.
Right. This means ensuring that from the very beginning, the proposed security requirements are deeply understood, accurately defined, and correctly documented. It's a critical pre-development step.
Makes sense.
It makes sure that whatever system or application you're about to create genuinely meets the true needs and expectations of the users and the business, aligning with their security demands and risk appetite.
So you're validating the concept itself.
You're essentially validating the concept and the entire set of requirements before committing significant resources to development. Think about designing a fortress. Validation would be ensuring you're building it in the right place for the right reasons, to protect against the right threats. Then, verification follows validation. This process addresses a related yet distinct question: are we building the product correctly?
Correctly. Okay, so how does that differ?
Well, once you've validated what needs to be built and its security requirements, verification confirms that the application or system is being constructed precisely according to those validated requirements and specifications.
According to the plan.
Exactly. It's about adherence to design documents, coding standards, security best practices, and architectural principles during the actual development and implementation phases.
So the build quality.
Right. Using our fortress analogy, verification would be ensuring that the walls are built to the specified thickness, the turrets are structurally sound, and the gates operate as designed. And crucially, both validation and verification aren't just isolated steps. They underscore the vital importance of early and continuous testing, not just a final check once something is fully built.
Continuous testing.
It's an ongoing process woven into every stage of development. You want to identify issues as early as possible when they are cheapest and easiest to fix.
So it sounds like the criticality or value of a system should directly influence how much effort we put into securing and testing it. Is that a fair principle to apply?
Precisely. That's a foundational principle that underpins all effective security assessment. The effort and resources you allocate to testing should always be directly proportionate to the value an application, system, or data holds for the organization.
So value isn't just dollars.
No, not at all. Value isn't just monetary worth. It encompasses critical business operations, sensitive customer data, intellectual property, brand reputation, regulatory compliance, all of it.
Right, the really important stuff.
Exactly. If a system handles sensitive customer financial data, for example, the depth and rigor of testing required will be far more intensive and continuous than for, say, a low-risk internal utility that simply manages office supplies.
Makes perfect sense.
This value-driven approach ensures that your security efforts and testing strategies are optimally aligned with business priorities, proving to stakeholders that these investments are indeed contributing positively to the business's resilience and success. It's about smart resource allocation where it matters most.
That's a clear guiding principle. Now, considering these foundational elements, what are the common testing strategies an organization might employ to achieve this kind of robust assurance?
Well, we can broadly categorize testing strategies across three main contexts: internal, external, and third-party. Each serves distinct purposes and offers unique benefits.
Okay, let's break those down. Internal first.
Sure. Let's start with internal audit. This type of testing is conducted by personnel within the organization itself, typically by an internal audit department or perhaps dedicated security team members.
People who work there.
Right. The results are primarily for internal consumption, aimed at finding improvements, identifying control gaps, and ensuring internal policies and procedures are functioning as intended.
So, self-improvement.
Exactly. For example, a publicly traded company typically has a much more rigorous internal auditing strategy than maybe a privately held one.
Why is that?
It's largely due to stricter regulatory requirements like Sarbanes-Oxley, SOX, compliance goals, and heightened accountability to shareholders. Their internal audit team is constantly assessing their own systems and processes, identifying areas of non-compliance or inefficiency, and recommending corrective actions. Then you have external audit. This scenario can unfold in one of two ways. Less commonly, it might involve someone internal examining an external service provider's controls, maybe as part of vendor risk management. However, more commonly, it involves your organization asking an unbiased external firm to come in and review your applications or systems.
Bringing in outside experts.
Exactly. These audits typically have a high degree of external validity and credibility because the auditors are independent. They have no inherent conflict of interest with your organization.
Which builds trust.
Right. It makes their findings more trustworthy and acceptable to outside parties, like investors, regulators, or even potential business partners. For instance, an external audit might be mandated by a bank regulator to ensure a financial institution's adherence to cybersecurity guidelines. And finally, there's the third-party audit. Here, three distinct parties are typically involved. The customer, the vendor, which is the service provider being audited, and an independent audit firm.
Three parties. Got it.
These audits are frequently initiated by one organization, the customer, to audit another, usually a service provider. The goal is often to demonstrate compliance with specific regulations, industry standards, or contractual obligations.
Like checking up on your cloud provider.
Exactly that scenario. If a company uses a cloud provider for its sensitive data, they would likely require a third-party audit of that cloud provider to ensure their data is protected according to agreed standards.
Okay.
Historically, audit standards for service organizations have evolved significantly in the U.S. We've moved from SAST 70 to SSE E16, and now the current standard is SSAE 18.
SSAE 18.
Yep. Outside the U.S., similar engagements are conducted under ISE 3402, but they're all commonly known as Service Organization Controls, or SOC reports.
SOC reports. Those come up all the time. Could you elaborate on the different types of SOC reports and what crucial information they cover for security professionals? They seem really important.
Certainly, SOC reports are absolutely critical, especially today, with so many outsourced services and cloud environments. So break them down.
Please do.
SOC 1 reports are quite specific. Their primary focus is on controls that might impact the accuracy of a service organization's financial reporting.
So about the money.
Essentially, yes. If your concern revolves around how a service provider's controls could affect your company's internal controls over financial reporting, a SOC 1 report is what you'd look at, very much about internal financial controls. SOC 2 reports, on the other hand, are generally what security professionals prioritize and find most valuable.
Okay, this is the one we really care about.
These are much more comprehensive. They concentrate on controls related to 5 key trust principles: security, availability, confidentiality, processing integrity, and privacy.
The trust services criteria.
Exactly. These reports delve deep into the operational effectiveness of a service provider's security program, covering aspects like access controls, incident response, data management, and much more.
Sounds detailed.
Very. The results of SOC2 reports are usually considered highly confidential and are shared under a non-disclosure agreement, or NDA, given the sensitive security information they contain. This is the report you'd want to see if you're assessing the security of a SaaS vendor, for instance. Then we have SOC3 reports. These are essentially stripped-down versions of SOC2 reports.
A lighter version?
Kind of. They also cover the 5 trust principles, but they are specifically intended for public disclosure and are often used for marketing purposes by service organizations.
Ah, so they can put it on their website.
Right. Because they're less detailed and designed for general public consumption, they offer significantly less granular insight into the actual control environment compared to SOC2. While they indicate a certain level of compliance, a discerning security professional would always push for SOC2 if they need genuine assurance.
So we have SOC 1, 2, and 3. And then I've heard there are also Type 1 and Type 2 reports within SOC 1 and SOC 2. That sounds like another layer of complexity. What's the distinction there, and why does it matter so much?
That's another crucial distinction, yes. It really determines the depth of assurance you receive from the report.
Okay.
A Type 1 report assesses the design of controls at its specific point in time. It's essentially a documentation review. The auditor looks at how the controls are designed on paper and whether they could be effective if implemented properly. Imagine reviewing the blueprints for a security system to see if the design looks sound.
So it doesn't say if they're actually working.
Exactly. It tells you nothing about whether those controls are actually operating effectively over a sustained period. It's just a snapshot of the design at that moment. A Type 2 report, however, goes much, much further. It examines not only the design of the controls, but, more importantly, their operating effectiveness over a period of time, typically over at least 6 months to a year. This means the auditor is observing, testing, and verifying that the controls are actually functioning as intended day in and day out throughout that specified period. They're looking at real evidence.
Evidence they work consistently.
Precisely. For security professionals seeking the most comprehensive assurance of operational security over time, SOC2 Type 2 reports are by far the most desirable.
SOC 2, Type 2. That's the gold standard then.
For operational assurance from service providers, it generally is. They provide concrete evidence of how controls performed over a sustained period, giving a much clearer, more reliable picture of a service provider's continuous security posture. That's vital for managing ongoing risk.
Given all these intricate strategies, reports, and distinctions, what's the security professional's specific active role in this entire ecosystem of assessment and testing? It sounds like they're more than just participants, right?
Oh, absolutely. Their role is central and crucial throughout this entire journey. They are the expert guides and the proactive problem solvers.
How so?
Well, security professionals are initially tasked with identifying risks within the organization. They are often the first to spot potential weaknesses, emerging threats, and areas of vulnerability based on their deep technical knowledge and understanding of the threat landscape.
Spotting the problems.
Yes. But beyond identification, they play a critical advisory role, guiding the design of testing processes. This ensures that these processes aren't just generic, but are specifically designed and executed in a way that appropriately evaluates those identified risks, targeting the most critical areas.
Making the tests relevant.
Exactly. And perhaps most importantly, they provide ongoing advice and practical support to stakeholders throughout the entire assessment and testing journey.
What kind of support?
Helping to interpret complex results, prioritize findings based on risk, and guide effective remediation efforts. They essentially translate the technical jargon into business impact, making the testing truly meaningful for the organization.
And does the physical location of the systems being assessed impact the strategy? For instance, whether they're housed in your own data center or perhaps hosted entirely in the cloud, how does that change the approach?
Yes, absolutely. The location where systems and data reside significantly impacts the scope, the approach, and even the tools used for the assessment. It really changes the game.
Okay, how?
Let's break down the 3 primary scenarios. On-premise assessments focus exclusively on evaluating the security measures and infrastructure of systems housed within an organization's own physical data centers and facilities.
Stuff you own and manage directly.
Right. This includes everything from the physical security of the building to network devices like firewalls and routers, individual servers, and the applications running directly within that owned environment. You have full control and thus full responsibility for securing every layer. In contrast, cloud assessments shift the focus entirely to data and applications hosted within a cloud service provider's environment, whether that's AWS, Azure, Google Cloud, or another provider.
The provider's infrastructure.
Exactly. Here, you're assessing the security configurations, controls, and critically, the shared responsibilities model between your organization and the cloud provider.
Shared responsibility is huge in the cloud.
It is. You're looking at things like virtual networks, cloud storage buckets, platform as a service offerings, serverless functions, all within the cloud context. The security approach here recognizes that some aspects are managed by the cloud provider, while others are entirely your responsibility. Finally, hybrid assessments are specifically designed to assess the connectivity and security measures that span both on-premise and cloud resources.
Bridging the gap.
Exactly. This examines how data flows securely between these two environments, how identity and access are managed across both realms, and the integration security controls that bridge your traditional on-premise infrastructure with your dynamic cloud services.
Which is super common now.
Increasingly common, yes, as organizations migrate to the cloud in stages or maintain hybrid environments long-term. Each of these scenarios, on-prem, cloud, hybrid, requires a distinct set of tools, expertise, and a nuanced understanding of where security responsibilities lie. 2. Hands-on security control testing, techniques and practices, 6.2.
Okay, that transitions us perfectly from the strategic planning of assessments to the actual conducting hands-on security control testing. Let's start with software, which is at the heart of so many systems today. Could you give us an overview of the different levels of software testing, maybe from individual components up to the entire system?
Certainly. When we talk about software testing, it's typically a layered and iterative approach that often mirrors the software development lifecycle itself. It starts small and builds up in complexity.
Layered. Okay. What's the first layer?
First, you usually begin with unit testing. This examines and tests individual, discrete components or units of an application as they are completed by a developer.
Testing the smallest pieces.
Right. It confirms that each specific piece of functionality, maybe a single function or a method, works as expected in isolation, independently of other parts of the system. For example, testing a single function that calculates a sum to ensure it consistently returns the correct value for various inputs. This is usually done by the developers themselves as they code. As more components are built and completed, you move to interface testing. This verifies how individual units or modules connect and communicate with each other through their standardized interfaces.
How they talk to each other.
Exactly. It ensures seamless and correct interaction between different parts of the system. For instance, if one component is designed to pass user authentication data to another component for verification, interface testing checks that the data is correctly transmitted, received, and interpreted, making sure the handshake between them works flawlessly. Next is integration testing. This focuses on testing groups of components or software units together, checking how they function as combined modules.
Putting the pieces together.
Yes. It's about ensuring that when units are put together, they still work correctly and don't introduce new issues or conflicts because of their interaction. This might involve testing how the user authentication module integrates with the user profile management module, verifying that a successfully logged in user can access and modify their profile without errors. Finally, at the highest level of software testing, there's system testing. This tests the entire integrated system as a whole.
The whole thing.
The whole thing. Verifying that the complete and integrated software product meets all its required specifications and functions as a cohesive end-to-end unit. This is often performed in an environment that closely mimics production.
Makes sense.
And it's crucial to remember that testing isn't just a final step before deployment. It's a continuous activity required during every stage of a system's lifecycle, right from the very beginning of its design and coding. The earlier you find a bug, the cheaper it is to fix.
That sounds like a very thorough and systematic process. When we're talking about the actual execution, what about the methods and tools used for these tests? Are we primarily talking about manual human effort, or is automation heavily involved in today's environment?
That's a great question. Both manual and automated techniques are absolutely vital and indispensable. Each brings unique strengths to the table.
So you need both.
Ideally, yes. Manual testing involves people actively performing tests. This could mean meticulously following specific processes, inspecting code line by line for subtle logic flaws, or entering various inputs into forms on a user interface to observe behavior.
Humans looking for problems.
Right. This human element is invaluable for spotting subtle usability issues, unexpected logical flaws, or complex scenario-based bugs that automated scripts might easily miss. It's also excellent for exploratory testing, where the tester is given free rein to sort of break the system in creative ways. Automated testing, on the other hand, leverages pre-written test scripts and specialized software to manipulate and execute tests automatically.
Letting the machines do the work.
Exactly. This allows for incredibly rapid, repeatable execution of a large volume of tests. It's especially crucial for regression testing, ensuring new code hasn't broken old functionality. Automated tests are perfect for repetitive, predictable checks and for integrating into continuous deployment, or CI/CD pipeline. The most thorough and effective testing strategies always employ a robust mix of both approaches. You use automation for speed and repeatability, and manual testing for deeper insights, creativity, and finding those harder to spot issues.
So a key distinction seems to be whether an application is running or not during testing. How exactly does testing an application while it's operational differ from testing it when it's static or not running? That seems like a pretty fundamental difference in approach.
It is a fundamental difference, and that's where static application security testing, Task-Dynamic Application Security Testing, DAST, come in. They represent those two distinct approaches.
SAST and DAST. Okay, let's start with SAST.
Okay. SAST, often referred to as static testing, or sometimes white box testing, is performed on the underlying source code, bytecode, or compiled application without the application actually running.
Testing the code itself.
Yes. Because the code is visible and accessible, SAST tools can perform a detailed, line-by-line examination for potential vulnerabilities directly within the code. They look for patterns indicative of weaknesses, like exploitable buffer overflows, common injection flaws, such as SQL injection, or syntax errors and insecure coding practices.
Like checking blueprints.
Exactly. It's like having the full architectural blueprints of a building and meticulously inspecting them to find structural weaknesses before construction even begins. SAST excels at identifying vulnerabilities early in the software development lifecycle, which is highly cost-effective.
Yeah.
But a drawback is it can sometimes have a high rate of false positives. In contrast, DAST, or dynamic testing, is performed while the application is running in a live or near-live environment.
So testing the running application.
Right. The focus here is on the application and system's observable behavior as the code executes, typically without access to the source code. This makes it a form of black box testing.
Black box, okay.
DAST tools interact with the application through its front end, much like a user or an attacker would. They send various inputs and analyze the responses to identify vulnerabilities that manifest during runtime.
Like what?
Things like cross-site scripting, XSS, authentication bypasses, or insecure server configurations. DAST is excellent at finding vulnerabilities that only appear when the application is actively processing data and interacting with other components.
Things SAST might miss.
Potentially, yes,
Yeah.
especially configuration issues or runtime behavior flaws. A really good example of dynamic testing is fuzz testing. Fuzz testing specifically is a powerful form of dynamic testing. It involves throwing random, unexpected, malformed, or oversized data inputs at an application to observe how it responds.
So throwing junk at it.
Pretty much. Seeing where it might break or behave unexpectedly, it's incredibly effective precisely because software tends to be designed with very logical, predictable inputs in mind. Fuzzing introduces chaos.
Chaos engineering, almost.
In a way, yes. It tries to overwhelm or confuse the application, revealing vulnerabilities that logical, expected input testing might completely miss. Think about sending an email with an attachment that has an impossibly long file name, or trying to send 10,000 characters to a field expecting only 50.
And there are different types of fuzzing.
Yes, two main types. There's mutation, or dumb fuzzing, which takes known, valid inputs and modifies them in various ways like flipping bits or changing data types. Then there's generational, or intelligent fuzzing, which develops inputs based on models of expected inputs or protocol specifications. This makes it more targeted and often more efficient at finding specific types of vulnerabilities.
So if I understand correctly, white box and black box testing really come down to the level of access you have to the application's internal workings during the test. Is that the main idea?
Exactly. That's the core distinction that defines the perspective of the tester and the information they have.
Okay, so black box.
Black box testing means you have no access to the internal structure, source code, or design documentation of the system being tested. You're testing it purely from an external perspective, simulating what an attacker with no prior knowledge would encounter. You interact only through its publicly available interfaces.
Simulating an outsider.
Right. This approach is excellent for discovering vulnerabilities that are exploitable from the outside, reflecting real-world attack scenarios. On the other hand, white box testing means you have full access to the source code, internal logic, design documentation, sometimes even development environment. This allows for a very detailed, granular examination of the internal structure, often from a developer's or an insider's perspective. It can uncover vulnerabilities that might not be visible or exploitable from the outside, but represent significant weaknesses in the internal design or implementation.
So both have value.
Absolutely. Both provide unique and valuable insights. In comprehensive security testing, they are often combined for a truly thorough assessment, giving you both an outsider's and an insider's view of potential weaknesses.
Beyond just running or not running and access to code, how else can systems be tested from a user's perspective once they are operational? You mentioned positive, negative, and misuse scenarios earlier. Can you elaborate on those and how they help uncover different types of issues?
Right. Once a system is operational and serving users, you can test it through scenarios that mimic how real users, both legitimate and malicious, might interact with it. These are typically categorized into three distinct ways.
Okay, what's the first?
Positive testing is about ensuring the system works exactly as expected when everything goes right, using normal, valid usage and inputs.
The happy path.
Exactly. It confirms that the system fulfills its intended functions and meets its requirements. For example, verifying that a user can successfully log in with correct credentials, create an account, or complete a purchase without any hitches. Confirming it does what it's supposed to do. Negative testing then focuses on how the system responds when normal errors or invalid inputs are intentionally introduced.
Testing for errors.
Yes. This helps identify the robustness of the system's error handling and its resilience to incorrect user actions. For instance, what happens if a user tries to enter letters into a numeric-only field? Does the system gracefully reject the input and provide a clear error message? Or does it crash or behave unexpectedly?
Or trying a bad password too many times.
Perfect example. Does it lock the account as expected? This type of testing ensures the system fails gracefully and securely when things go wrong. And then there's misuse testing, which is also known as abuse case testing. This is where you adopt the mindset of someone intentionally trying to break, compromise, or attack the system.
Thinking like an attacker.
Precisely. It helps to understand vulnerabilities from an attacker's viewpoint, aiming to cause integrity failures, malfunctions, or unauthorized access. An example would be attempting to bypass an input validation check by entering malicious characters or carefully crafted SQL code into a web form.
Like trying a SQL injection.
Exactly. Simulating a potential SQL injection attack to see if the system's defenses can withstand it. This is crucial for identifying how an attacker might exploit flaws that aren't apparent from normal, legitimate use.
These sound like very effective ways to find problems. But when you're dealing with potentially millions of possible inputs, how do you make all this testing more efficient without compromising coverage? Are there techniques to minimize the number of test cases while still being thorough?
Yes, absolutely. Efficiency is key. Equivalence partitioning and boundary value analysis are two widely used and highly effective techniques specifically designed for this. They make testing more efficient by intelligently reducing the number of test cases needed.
Okay, how do they work?
Both techniques build on the idea of identifying boundaries, points where changes in system behavior are expected to occur. Boundary value analysis then focuses your testing specifically on the values at and on either side of these boundaries.
Testing the edges.
Exactly. The core reasoning here is that historical data shows bugs are most likely to exist at these extreme points rather than in the middle of a valid range.
Makes sense.
So for example, if a data field accepts numbers from 1 to 100, you wouldn't test every single number. Instead, you test values like 0, just below minimum, 1 minimum, 2, just above minimum, 99, just below maximum, 100, maximum, and 101, just above maximum. This small set of tests covers the most common points of failure efficiently. Equivalence partitioning takes it a step further. After identifying boundaries, it identifies partitions or groups of inputs that are expected to exhibit the exact same behavior.
Grouping similar inputs.
Right. Once you've defined these partitions, you only need to test one representative input from each partition, knowing that all other inputs within that same partition will likely behave similarly.
So you don't need to test everything in the group.
Correct. For instance, if any number between 1 and 100 is treated identically by the system, you might just pick 50 as your single test input for that entire range. Similarly, if negative numbers, 0, and positive numbers are distinct categories, you'd pick one input from each. This significantly streamlines testing by avoiding redundant tests on inputs that are functionally equivalent.
That makes a lot of sense for efficiency. But how do we actually know if we've tested enough of the code? Is there a quantifiable metric that tells us about the thoroughness of our testing effort?
That's precisely where test coverage analysis comes in. It's a quantifiable metric, often expressed as a simple mathematical formula.
A formula?
Yeah, basically. The amount of code covered by your tests divided by the total amount of code in the application. That gives you a percentage.
A coverage percentage.
Right. This provides an objective insight into how much of the application's source code has been actually exercised by your test suite. It's a crucial indicator for gauging the thoroughness of your testing and helping to identify areas of the code base that might have been missed or insufficiently tested.
And there are different ways to measure coverage.
Yes, there are common criteria used for this analysis. For example, branch coverage. This metric checks if every branch in your code typically associated with IF statements or other conditional logic has been executed under all its possible conditions, meaning both the IF path and the LSE path have been traversed by tests.
Testing both sides of an IF.
Exactly. If you have an if condition do this statement, you need tests that make condition true and tests that make it false to achieve full branch coverage.
Right.
Then there's condition coverage. This goes a bit deeper, especially with complex logical expressions like if, A, and D. It checks if every individual logical condition within that expression, A, B, has been evaluated to both true and false by your tests.
More granular.
A bit, yes. There's also functional coverage. This is a higher level measure, verifying if every function or method in the code has been called at least once by your tests and returned results. It confirms that the core functionalities are at least being invoked. Loop coverage is another one. For code segments involving loops, like for or while loops, this ensures that every loop has been executed multiple times, exactly once, and ideally, not at all if the logic allows, to test its different states and edge cases. And finally, the most basic form is statement coverage. This simply checks if every executable line of code has been run at least once during your tests.
So did the test hit this line of code?
Pretty much. A comprehensive test coverage report details all these metrics. It guides developers and security teams to improve the completeness of their test suites and reduce the risk of undiscovered vulnerabilities hiding in untested code.
This brings us to two terms often used interchangeably, but which I suspect have very distinct meanings in the security world: vulnerability assessments and penetration testing. What's the core difference between them, and why is it important to understand that distinction?
You're right to highlight the distinction. They are indeed very different processes, although both aim to identify weaknesses. Understanding the difference is crucial for setting expectations and allocating resources effectively.
Okay, so what's a vulnerability assessment?
A vulnerability assessment is primarily about identification and reporting. It involves using automated tools, and often some manual checks, to identify known vulnerabilities, misconfigurations, and weaknesses within systems, applications, or networks.
Finding the problems.
Finding them, yes. It then generates a comprehensive report of those findings, detailing the weaknesses, their severity, and sometimes recommendations for remediation. But critically, no further action is taken to exploit them.
Just finding and reporting.
Exactly. Imagine a doctor conducting a thorough checkup, identifying a patient's susceptibility to a certain illness or a lifestyle factor that might lead to health issues. They found a weakness, noted it, and reported it, perhaps with advice for prevention. These assessments are typically faster, less resource-intensive, and often performed regularly, maybe quarterly or monthly. A penetration test, on the other hand, goes a crucial step further. After identifying potential vulnerabilities, an active attempt is made to exploit each one.
Trying to break in.
Yes. To see if a breach or compromise can actually be achieved. This is a simulated, ethical hack designed to test the resilience of your defenses in a real-world attack scenario.
Like the doctor example.
Right. It's akin to that doctor actively trying to, say, expose the patient to a controlled amount of the allergen to see if they actually have a reaction, testing if their immune system or preventative measures hold up.
Much more active.
Much more active, yes. Penetration tests are typically much more manual, complex, and therefore take longer, often several days or even weeks, depending on the system's complexity and the scope. The typical stages for both vulnerability assessments and penetration tests include reconnaissance, gathering info, enumeration, active discovery, vulnerability analysis, identifying weaknesses. Then comes exploitation. This is the key pen test exclusive step, attempting to break in. And finally, reporting.
So a penetration test is essentially simulating a real attack to see how far an attacker could potentially get. That's quite a proactive approach. What variables come into play when planning and executing these simulated attacks? Seems like there'd be different ways to do it.
Exactly. It's the ultimate test of your security posture against a simulated live threat. And yes, there are several key variables that significantly influence how these tests are conducted, dictating the scope, realism, and insights gained. These variables include the perspective, the approach, and the knowledge given to the assessors.
Okay, let's take those one by one. Perspective.
First, perspective refers to where the test is performed from, mirroring different attacker origins. Internal testing means the penetration test is conducted from inside the corporate network.
Simulating an insider threat.
Exactly, like a disgruntled employee or perhaps an attacker who has already successfully breached the perimeter defenses. This assesses lateral movement capabilities and the effectiveness of internal controls.
And external testing.
External testing means the test is performed from outside the network, typically from the internet. This considers threats that originate from external malicious actors trying to gain initial access. Next, the approach dictates how much the assessor knows about the target environment at the outset of the test.
How much info they start with.
Right. Blind testing means the assessor has very little to no information about the target organization or its systems being tested. This simulates a true external attacker who must gather all information from scratch, relying solely on publicly available data and their own reconnaissance efforts. It offers the most realistic view of an unknown external threat.
And double blind. That sounds intense.
It is. Double-blind testing goes even further. Not only does the assessor have little to no information, but neither the target company's IT nor security operations teams know about the upcoming test.
Wow, so the defenders don't know it's a test.
Correct. This is an exceptional way to assess the organization's real-world incident detection and response capabilities in a completely realistic, unannounced scenario. It really tests your SOC's effectiveness. Finally, knowledge refers to the level of information given to the assessor prior to the test. This aligns with the box colors we discussed.
Ah, black, white, gray box again.
Exactly. Zero knowledge is synonymous with black box testing, or the blind approach. The assessor starts with absolutely no internal information. Partial knowledge, often referred to as gray box testing, means the assessor is given some limited information.
Like what?
Maybe network diagrams, specific application architecture details, or a few user credentials, but not full comprehensive details. This balances the realism of black box with the efficiency of white box, allowing the tester to delve deeper more quickly.
And full knowledge.
Full knowledge, or white box testing, means the assessor is given complete details about the target environment. This could include IP ranges, detailed network diagrams, info about critical systems, maybe even password policies, or access to source code. This allows for a very deep and thorough examination of internal logic, configurations, and potential weaknesses that might be missed in a black box test due to lack of visibility. Each variable has a place in a comprehensive security testing program.
Once all these vulnerabilities are found, whether through an assessment or a penetration test, the work isn't over. What's the comprehensive process for managing these identified weaknesses effectively over time? You can't just find them and forget them.
Absolutely not. That's where vulnerability management becomes absolutely critical. And it's essential to understand it as a cyclical, continuous process, not a one-off activity. An effective vulnerability management program is dynamic and iterative, always adapting.
A cycle. What are the steps?
At a high level, a robust program should consistently include 4 key components. First, you need an accurate and up-to-date inventory of all assets in the organization. You simply cannot protect what you don't know you have.
Know what you own.
Exactly. Servers, workstations, cloud instances, mobile devices, applications, IoT devices, everything. Maintaining this inventory is foundational. Second, for each asset in that inventory, you must accurately identify its value or criticality to the organization. Not all assets are equally important.
Prioritization based on importance.
Right. Is it a mission-critical database?
Yeah.
A development server? A public-facing web server? This prioritization based on business impact is crucial because it directly informs and prioritizes your remediation efforts. You fix the most critical vulnerabilities on the most critical assets first. Third, you move to the core of the process, identifying vulnerabilities for each asset and then planning their remediation. This involves leveraging scanning tools, manual assessments, documenting findings, prioritizing them based on severity and asset criticality, and then assigning responsibility for fixing them.
The actual fixing part.
This is where the rubber meets the road. You're documenting, prioritizing, and assigning the actual fixes. And finally, there's the ongoing review and assessment of all these steps. This is why it's a cycle. New vulnerabilities emerge constantly. Systems change. Old vulnerabilities might resurface.
It never really ends.
Pretty much.
Yeah.
So you're continuously scanning, reassessing, patching, and verifying to ensure that your security posture remains strong. It's truly a continuous loop of identify, prioritize, remediate, and verify.
And what specific tools and standardized systems are typically used to identify these vulnerabilities in the first place, and then to interpret and prioritize the findings? You need some structure for that.
Definitely. To identify vulnerabilities, vulnerability scanning is a key automated tool. It's designed to probe systems, applications, and networks for known weaknesses. Things like missing security patches, common misconfigurations, or known faulty code.
Automated checks.
Right. And there are two primary types of scans based on access level: credentialed or authenticated scans. These use valid credentials, often read-only accounts, to log in and access deeper layers of the system.
Getting an inside look?
Yes, this allows for a much more accurate and comprehensive assessment, simulating an insider or a compromised account. They can identify misconfigurations that aren't externally visible. Then there are uncredentialed or unauthenticated scans, which are performed without any credentials.
The outside view.
Exactly, simulating an external attacker's view. These are good for seeing what an external threat could detect easily. Beyond scanners, other active reconnaissance tools are used. For example, banner grabbing.
Banner grabbing.
Yeah, it's a simple but effective technique used to identify a system's operating system, specific applications, and their versions by examining network banners. These are messages sent by network services like web servers or FTP servers that often reveal identifying information.
Like reading the welcome message.
Kind of. Similarly, OS fingerprinting works by identifying the unique characteristics of a system through how it forms network packets or responds to certain probes. This can reveal details about the underlying operating system and often its version, which helps in identifying known vulnerabilities associated with that specific OS version. Now, for interpreting and understanding the results from all these tools, we use standardized systems. They provide a common language and a consistent way to score severity.
Okay, like what?
CVE, Common Vulnerability and Exposures, is a big one. It's a publicly available dictionary or list of publicly known cybersecurity vulnerabilities. Each CVE entry has a unique ID number, a description, and references. It provides a common language for discussing specific vulnerabilities, which is invaluable for threat intelligence and patching.
So everyone's talking about the same flaw.
Exactly. Complementing CVE is CVSS, Common Vulnerability Scoring System. This provides a standardized open scoring system for vulnerability severity.
A score, like 1 to 10.
Generally, yes, usually on a 0 to 10 scale. It calculates a score based on various characteristics like exploitability, how easy it is to exploit, impact, what happens if it's exploited, confidentiality, integrity, availability, and sometimes environmental factors specific to your organization.
Helping prioritize.
Precisely. It helps organizations prioritize vulnerabilities based on their potential risk rather than just their technical complexity. A SQL injection might score high because its exploitability is high and its impact on data confidentiality is severe. And it's also crucial for any security professional to understand two common issues with scanning: false positives and false negatives.
Right, those can be tricky. False positive.
A false positive occurs when the system claims a vulnerability exists, but in reality, it doesn't.
The standard cried wolf.
Exactly. While annoying because they require manual verification and waste time, these are generally less dangerous.
And false negative.
False negatives are particularly dangerous. This is when the system indicates that everything is fine and no vulnerability exists, but in reality, there is one.
The scanner missed something important.
Right. These are critical because they give a false sense of security, leaving real attack vectors open and unnoticed. They're a significant blind spot.
I've heard quite a bit about red teams and blue teams in this context of security testing and operations. What exactly are those, and what distinct roles do they play within an organization's security framework?
Yes, red and blue teams. These terms are fundamental to understanding modern security exercises and operations. They represent distinct, often adversarial functions within security testing.
Adversarial, like they fight each other.
In a simulated way, yes. The red team is the offensive security team. Their role is to simulate hackers or real-world threats, actively working to find weaknesses and penetrate an organization's defenses. The ethical attackers, yes. Their focus is on ethical hacking, conducting penetration tests, employing social engineering tactics, and leveraging threat intelligence to mimic the techniques, tactics, and procedures, DTPs, of actual malicious actors.
Yeah.
They are the attackers in the exercise, trying to achieve specific objectives like data exfiltration or system compromise. In contrast, the blue team is the in-house defensive security team. Their primary role is to stop those threats, detect attacks as they happen, and respond effectively to incidents.
The defender.
Exactly. They focus on continuous security monitoring, incident response planning and execution, digital forensics, and overall security operations. They are the defenders responsible for maintaining and improving the organization's security posture day to day. They build, operate, and refine the security controls that the red team tries to bypass. Now, the purple team isn't usually a separate third team in the traditional sense.
Not another color.
Not usually. It represents the crucial collaboration and communication between the red and blue teams. It's a strategic approach focusing on information sharing, continuous feedback loops, and fostering a healthy competition to improve the overall security posture.
Making them work together.
Right. Purple team exercises ensure that the red team's findings directly lead to blue team improvements. For example, the red team bypassed this control. The blue team now knows how to harden it or improve detection. And vice versa. The blue team's insights on detection capabilities inform the red team's attack simulations. This continuous feedback loop creates a much more effective and adaptive security defense than if they operated in isolation.
That makes perfect sense for continuous improvement. And speaking of continuous, what about automating some of these penetration testing aspects? Is that possible, or is it always a manual, human-driven process? Can machines do pen tests?
It's a great question, and yes, automation is playing an increasingly important role, though it doesn't entirely replace human ingenuity, especially for complex scenarios. That's where breach and attack simulation, BAS platforms, come in.
BAS platforms.
Okay. These platforms aim to automate aspects of penetration testing and validate security controls continuously. It's important to clarify, though, they aren't typically waging actual full-blown creative attacks in the way a human penetration tester would.
So what do they do?
Instead, BAS platforms conduct automated, continuous testing of security controls to identify deficiencies in real time. They simulate known attack behaviors. A BAS system effectively combines elements of red team, attack simulation, and blue team, control validation techniques, with sophisticated automation. It simulates advanced threats running against the environment by injecting specific threat indicators or known attack scenarios.
Like running known malware patterns.
Exactly. It might simulate a specific type of malware attempting to communicate with a command and control server or a common phishing exploit technique. The platform then verifies whether your existing security controls, like firewalls, EDR, SIEM rules, successfully detected, prevented, or contained the simulated attack.
So it checks if your defenses work against known tactics.
Precisely. It's about providing continuous validation of your security posture against known TTPs without the need for constant resource-intensive manual penetration tests. This allows organizations to proactively identify gaps in their defenses against common attacks and remediate them before a real attacker exploits them.
So after all this active testing and simulation, where does something like log review fit into the picture? It seems like a more passive activity than direct penetration testing, but I imagine it's still fundamental.
You're absolutely right. Log review and analysis is, in fact, fundamental and incredibly critical. It's a best practice for every organization, despite maybe appearing passive compared to active testing.
How is it active then?
Well, while it doesn't actively test a system's resilience in the same way a pen test does, it's profoundly active in terms of detection, investigation, and maintaining security visibility. Logs are the digital breadcrumbs of everything that happens on your systems and networks.
The evidence trail.
It's exactly. They should be relevant, actively and proactively reviewed, and especially scrutinized for errors, unusual patterns, and anomalies that could point to problems, unauthorized modifications, policy violations, or even ongoing breaches. They provide the essential forensic trail for incident response. A key aspect of effective log management is ensuring synchronized log event times. This is huge.
Getting the timestamps right.
Yes. If you have multiple devices, servers, firewalls, switches, applications, all logging events, their timestamps must be consistent across the entire infrastructure. This is typically achieved using Network Time Protocol,
NTP.
NTP for time sync.
Right. It ensures all system and device clocks are set to the exact same, highly accurate time. This consistency is absolutely critical for correlating activities across different systems, especially during a breach investigation. Imagine trying to piece together an attack timeline if logs are out of sync. It becomes nearly impossible. Log data is generated by virtually every system operating within an organization, from endpoints to network devices to applications. The full logging and monitoring process is comprehensive. What does it involve?
It encompasses several stages: generation, the log data itself; transmission, securely sending logs centrally; collection, aggregating them; normalization, standardizing formats; analysis, looking for patterns and events; retention, storing for compliance forensics; and ultimately secure disposal. Now, to manage and analyze this vast, constantly growing amount of log data efficiently, security information and event management. These sophisticated platforms collect, aggregate, normalize, correlate, and securely store log data from across the entire IT environment. They apply rules and analytics to spot patterns, alert on anomalies, and provide a holistic, real-time view of security events.
Helping security teams see the big picture.
Exactly, allowing security teams to detect and respond to threats much more quickly and effectively than manual review ever could.
What about testing systems when they are already up and running and actively serving users? Are there specific techniques tailored for that operational live environment? Testing in production.
Yes, absolutely. That's what we refer to as operational testing. It's performed specifically when a system is in live operation and users are interacting with it. Two common and highly valuable techniques are often employed here.
Okay, what are they?
First, there's real user monitoring, RUM. This is a passive technique. It monitors actual user interactions and activity with a website or application in real time.
Watching what real users do.
Yes. It captures data on how real users experience the system, page load times, errors encountered, navigation paths, overall responsiveness. RUM provides invaluable insights into performance and usability issues from the perspective of your actual user base.
How does that relate to security?
Well, while often associated with performance, it can indirectly reveal security issues. For example, if users are experiencing frequent errors on secure pages or unexpected redirects, that could signal a problem. It's often seen as a process that starts pre-deployment but definitely continues into production, using the actual user interface to confirm proper behavior under real load. The second technique is synthetic performance monitoring. This is often referred to as synthetic transactions or simply synthetic monitoring.
Synthetic, like fake users.
Kind of. It involves creating automated test scripts for specific critical functionalities like logging in, adding an item to a shopping cart, submitting a form, or performing a specific search query. These scripts are then run automatically at regular intervals, often from various geographic locations.
Running automated tests against the live site.
Exactly. To examine functionality and performance under load, it synthetically simulates user behavior. For the highest accuracy regarding performance and availability, it's often best performed directly in a production environment.
Why production? Seems risky.
It needs careful implementation, but production is where the true real-world performance and security posture will be measured. It allows you to detect issues like slowdowns or functionality breaks before your actual users do. These simulated transactions can alert you proactively.
And what if a system or application is updated, patched, or undergoes any kind of change? Does it need to be completely retested, or is there a specific type of testing that focuses on ensuring existing functionality isn't broken by the change?
Absolutely. Retesting after changes is non-negotiable and critically important for maintaining system stability and security. That's precisely where regression testing comes in.
Regression testing, okay.
It's the systematic process of verifying that previously tested and functional software still works correctly and is expected after any updates, enhancements, bug fixes, or patches have been applied.
Making sure you didn't break something else.
Exactly. The primary concern is that new changes, even seemingly minor ones, might inadvertently introduce new bugs, or worse, break existing functionality that was previously working perfectly fine. This phenomenon is often called a breaking change, or simply a regression. So, after any modification to the code or configuration, whether it's a security patch, a new feature, an OS upgrade, or a bug fix, regression testing ensures that the new changes haven't negatively impacted the system's stability, performance, or existing features.
How is it done? Rerun all tests?
Not necessarily all of them. It typically involves rerunning a carefully selected subset of previously executed test cases that cover the core functionalities and areas potentially impacted by the change. If these tests pass, it gives confidence that the system's core functionality remains intact. It's a vital safety net in continuous development and operations. DevOps, DevSecOps.
Finally, how do organizations ensure all this testing, all these controls, and all these rigorous processes align not just with internal rules, but also with external regulations and industry standards? What ties it all together from a compliance perspective?
That's the vital and ongoing role of compliance checks. These aren't a separate phase, but rather an integral and continuous part of the security control testing process itself.
Checking against the rules.
Precisely. Their purpose is to confirm that implemented controls and their resulting outputs align perfectly with documented security requirements, organizational policies, industry standards, like PCI DSS for credit cards, or regulatory mandates, like GDPR or CCPA, and established security baselines. It's the binding element.
The glue holding it together.
You could say that. It ties all the individual security activities together, ensuring adherence to established guidelines and legal obligations. Organizations typically create and meticulously maintain detailed compliance plans that map their specific obligations to their implemented controls.
Mapping rules to controls.
Yes. Then, they continuously verify that those controls are functioning properly and effectively meeting those requirements through testing and auditing. This isn't just about avoiding fines, it's about building trust, demonstrating due diligence, and ensuring your security posture is not only technically sound, but also legally defensible and aligned with external expectations. 3. The data behind security. Collecting and utilizing process data. 6.3.
Okay, so all this extensive testing generates a massive amount of data, just mountains of it, I imagine. How do security teams effectively utilize this wealth of information to make informed decisions, set strategic goals, and truly understand their security posture over time?
That's a critical point. The data collected from security processes is absolutely crucial. It's not just about collecting logs, it's about using that data to inform strategic decision-making, set realistic security goals, plan targeted actions, and continuously review performance.
Turning data into action.
Exactly. We primarily look in two distinct but complementary types of metrics here: key risk indicators, KRIs, and key performance indicators, KPIs.
Okay.
They serve different but equally important purposes.
KRIs and KPIs, let's break those down. KPIs first.
Sure. KPIs, or key performance indicators, are fundamentally backward-looking metrics. They are designed to indicate the achievement of performance targets or provide insights into risk events that have already affected the organization.
Looking back at what happened.
Right. KPIs tell you how well your security processes have performed historically. For example, a KPI could be the number of open vulnerabilities at a given time, indicating your security debt backlog, or the average time it takes your team to resolve critical vulnerabilities that reflects efficiency. The number of compromised accounts detected over a quarter, the percentage of employees who completed mandatory security awareness training, or the number of detected software flaws found by SAST in pre-production code scanning. They are about measuring past performance and current state, essentially telling you, this is how we've done so far. KRIs, or key risk indicators, on the other hand, are forward-looking metrics.
Looking ahead.
Yes. They are designed to indicate the level of exposure to potential operational risk in the future. KRIs help security leaders monitor potential future shifts in risk conditions or identify new emerging risks before they manifest as actual incidents. They're like early warning signs.
Predicting potential problems.
Exactly. For instance, a KRI might be the number of mission-critical systems running outdated software that will soon reach end of life and become unsupported. That signals future vulnerability. Or maybe the percentage increase in external scanning attempts against your public-facing web applications, indicating a rise in hostile interests.
So they prompt proactive action.
That's the goal. They aim to provide an early warning signal, prompting proactive measures. They tell you, this is where we might be vulnerable in the future. Now, when defining these metrics, whether KPIs or KRIs, it's highly beneficial to follow the widely accepted SMART criteria. This ensures they are actionable and meaningful.
SMART criteria. Remind us what that stands for.
Sure. Specific, the result is clearly stated, unambiguous. Measurable, the data can actually be collected, quantified, and tracked. Achievable, the targets are realistic and can actually drive desired outcomes. Relevant, the metric is aligned directly to the overall business strategy and what's most important. And timely, the results are available when needed for decision-making, not weeks later.
Specific, measurable, achievable, relevant, timely.
Got it. Adhering to SMART criteria ensures your metrics are powerful tools for guiding security strategy, not just numbers on a dashboard.
That's a very clear way to differentiate KRIs and KPIs and ensure they're actionable. Given all the possibilities, though, how does an organization actually decide what specific metrics to focus on? What drives that selection process? There must be hundreds you could track.
You're right, there are countless possibilities. It all boils down to their unique business goals, their specific objectives, and their acceptable risk appetite. What's most important to them to protect, and what risks are they most concerned about?
Tailored to the specific business.
Exactly. The metrics chosen should always directly align with the organization's strategic priorities and its risk management framework. For example, metrics might be tailored to focus on several critical areas of security. Let's consider account management. This is crucial because, as we know, a significant percentage of successful breaches involve compromising existing privileged accounts or escalating privileges from regular accounts.
Always a target.
Always. So metrics in this area would focus on ensuring only authorized users have access, that privileged accounts are handled securely with MFA and strict controls, and that regular reviews of user permissions happen.
Checking who has access to what.
Right. KPIs here might be the number of dormant or orphaned accounts, or the time taken to deprovision accounts. KRIs could be the number of privileged accounts without multi-factor authentication enabled. Then there's management review and approval. This ties into that continuous improvement cycle we talked about.
And PDCA cycle.
Exactly. Metrics here would show the effectiveness of regular reviews by leadership to ensure security policies are followed, permissions are appropriate, and unauthorized changes don't occur. It connects directly to the Plan-Do-Check Act loop from standards like ISO 9000. Check is security assessment and testing, and APT is the management review taking corrective actions based on those findings, feeding back into the plan stage. Backup verification is another vital area. You need metrics here.
Just knowing backups ran isn't enough.
Not really. Metrics here would focus on periodically inspecting backup results to ensure data protection processes are truly effective, and that data can actually be recovered. This could involve reviewing logs of successful backups, yes, but also comparing hash values of backed up data for integrity, or even performing actual data restores.
Test restores are key.
Absolutely. Confirming data integrity and recoverability within defined recovery time objectives, RTOs. A key metric would be the success rate of those test restores. Training and awareness is also paramount, and you need metrics to evaluate its effectiveness.
How do you measure that?
Well, tracking completion rates of training modules is a basic KPI. But more dynamically, assessing employee behavior through simulated phishing attacks is critical. Ensure they understand current threats and apply best practices. The click-through rate on phishing simulations could be a very insightful KRI, and critically, disaster recovery, DR, and business continuity BC. These are related but distinct.
What's the difference again?
DR focuses specifically on restoring information technology systems after a disaster, getting the tech back online. BC takes a broader, holistic view, ensuring vital business processes remain unaffected or can be quickly restored, even if the IT systems are still recovering.
Business first, then IT.
In terms of scope, yes. Both programs need rigorous, regular assessment and testing. Metrics would show actual recovery times achieved versus objectives, RTOs, and recovery point objectives, RPOs, and the overall business impact of simulated outages.
And safety first.
Always. It's vital to remember that in any disaster scenario, the protection of human life and safety comes first before the recovery of material assets for IT systems. That's the absolute priority.
It truly sounds like a holistic approach is needed, tying every security activity and every metric back to the organization's overarching strategic goals and risk appetite, rather than just performing isolated technical checks. The P, actioning results and audit facilitation, 6.4 and 6.5. Okay, so once all the rigorous testing is complete and this rich, detailed data is collected and thoroughly analyzed, what happens next? How do you move beyond simply having a list of findings and actually generate a report that truly makes a tangible difference and drives meaningful action within the organization? That seems like the hard part.
It is a critical part, certainly. This is where the real value of assessment and testing comes to fruition. The ultimate goal of the analysis phase is to logically proceed from raw facts, all those technical data points you've painstakingly gathered, to truly actionable information that resonates with decision makers.
From facts to action.
Exactly. It's really a three-step process, each building on the last. Step 1. You must diligently review and thoroughly understand the raw data. This means going through every single finding from your scans, pen tests, log reviews, monitoring, compliance checks. You need to grasp the technical details.
Oh.
What was found, the specific system affected, the precise nature of the vulnerability or control gap. This is the what did we find phase. Pure facts. Step 2. This is perhaps the most crucial step and one sometimes overlooked by very technical folks. You must determine the business impact of those facts.
The so what question.
Yep, exactly. The so what question that leadership will inevitably ask. A raw list of technical vulnerabilities, no matter how severe they seem technically, is of little value to business leaders unless it's translated, put into a clear business context they can immediately understand.
Speak their language.
Right. You need to explain how a technical finding affects operations, finances, reputation, customer trust, or regulatory compliance. Instead of just saying SQL injection vulnerability found, explain, this means customer credit card data could be stolen, potentially leading to significant PCI DSS fines, severe brand damage, and loss of customer loyalty. Connect technical risk to tangible business consequences. Step 3. Based on that clearly articulated business impact, you must then determine what is truly actionable. The results are only valuable if they lead to concrete, prioritized steps the organization can actually take to effectively improve its security posture.
Real solutions.
Yes. This means prioritizing findings based on that blend of technical severity and business impact, and then outlining specific, realistic, and measurable recommendations for remediation. The report should offer solutions, not just point out problems.
That's a very clear pathway from data to decision. So what are those key actions that typically come out of this comprehensive analysis once findings are prioritized and understood in a business context? What happens with the vulnerabilities?
3 critical areas typically emerge: defining how an organization responds to identified vulnerabilities and control gaps, remediation, exception handling, and ethical disclosure. Remediation is the most direct and common action. This involves meticulously documenting and then implementing the specific steps required to fix all identified vulnerabilities and address control deficiencies.
Fixing the problems.
Right. And it's important to remember that in many organizations, the majority of vulnerabilities often stem not just from pure software defects, but more commonly from misconfigured systems, inadequate security policies that aren't being followed, maybe unsound business processes, or simply staff who are unaware of security best practices.
So it's not always just code bugs.
Often not. Therefore, effective remediation should be a collaborative effort involving all relevant stakeholders across the organization. IT, security, developers, business owners, maybe even HR for training. Not just an isolated IT or security task. It's a collective responsibility to fix the root causes. Then there's exception handling. Sometimes an identified vulnerability cannot be immediately patched or remediated for legitimate reasons.
Like when you just can't patch it right now.
Exactly.
Yeah.
Maybe the system is extremely critical and can't have downtime. Or perhaps there are no patches available for old end-of-life software. Or it could be a specialized device, like in manufacturing or healthcare, that requires costly and lengthy reaccreditation after any change.
So what do you do then?
In such cases, the vulnerability must be formally documented. The reason for not remediating needs to be clearly noted and approved by the appropriate risk owners. And critically, compensatory controls must be implemented.
Compensatory controls, like workarounds.
Kind of. They are alternative security measures taken to address the weaknesses or to compensate for the inability to meet a specific security requirement directly. Examples could include microsegmentation, isolating the vulnerable device from the rest of the network, or implementing strict access restrictions, limiting who can connect to it, or maybe enhanced monitoring around it to detect any attempts to exploit the known vulnerability. This acknowledges the risk and manages it differently, rather than just ignoring it. And finally, ethical disclosure. This is important. If security professionals during their testing or assessment activities discover a previously unknown vulnerability, what's often called a zero-day, that points to a significant flaw in widely used software or hardware.
Something nobody knew about before.
Right. They have a professional and ethical responsibility to report it responsibly. This typically means making a private, responsible disclosure to the affected vendor first.
Tell the vendor privately.
Yes. Providing them with a reasonable amount of time, often industry standards suggest 60 or 90 days, sometimes more depending on complexity, to create a patch or remediation. The goal is to allow the vendor to fix the issue discreetly before it can be widely exploited by malicious actors.
What if the vendor doesn't act?
Well, if the vendor fails to act within that reasonable time frame and there is a significant risk to the public or other users, then public disclosure may be warranted. This is done to protect other users and customers who might otherwise remain exposed to the unpatched vulnerability. It's a very carefully considered last resort step, usually following established disclosure policies.
Now let's talk about audits themselves again. We discussed internal, external, and third-party strategies earlier. But how do the actual execution and characteristics of internal audits compare to external or third-party audits in practice? What are their distinct advantages and disadvantages when you're the one undergoing the audit?
That's a good perspective to take. Each type of audit definitely feels different and has distinct characteristics, advantages, and disadvantages depending on the organization's needs, resources, and the audit's context. Let's look at internal audits again. Conducted by the organization's own staff or internal audit department, their purpose is often internal improvement, policy adherence checks, and maybe validating controls before an external audit.
The pros.
The advantages are significant. The internal team has a deep, innate understanding of the internal environment, systems, processes, culture. This naturally reduces the time needed for them to get up to speed. They can often delve into all parts of systems due to their insider knowledge and access, and they can sometimes be more agile, perhaps rescheduling failed tests quickly.
On the cons.
There are notable disadvantages, too. The internal team might have limited exposure to new methodologies or technologies compared to external auditors who see many environments. So maybe depth, but not breadth of experience. There's also the potential for conflicts of interest or a reluctance to report negatively on internal colleagues or teams. And sometimes, maybe unintentionally, internal auditors might start with an existing agenda, which could subtly skew findings. External audits, sometimes called second-party audits, are conducted by or on behalf of a business partner, like we mentioned.
Tied to contracts.
Right, typically tied directly to contractual obligations. A customer auditing a supplier, perhaps. They're strictly scoped to include only what's contractually required. They offer an independent perspective that an internal audit cannot, providing external validation for specific requirements, and third-party audits, conducted by completely independent firms like the ones issuing SOC reports, often required for regulatory compliance or industry standards.
The advantages here.
Strong advantages. These firms likely have broad experience auditing many types of systems and organizations, bringing a vast knowledge base. Critically, they are not affected by internal dynamics or politics, ensuring unbiased and highly credible findings that external parties generally accept.
Sounds good. Any downsides?
Yes, disadvantages exist. The most prominent is cost. Third-party auditors are significantly more expensive than using internal teams, which often means less frequent audits can be performed. Also, even with an external firm, your internal resources are still required to assist them, providing documentation, answering questions, guiding them. That adds a substantial internal overhead and burden on your staff.
And does the physical location of the systems also play a role in audits, similar to how it impacts assessments? Does an audit of an on-premise system look different from one in the cloud from the auditor's perspective?
Yes, absolutely. Just as with security assessments, the same distinctions and considerations apply directly to audits based on the environment and location. The environment fundamentally dictates the scope, the specific controls the auditors need to examine, and the challenges involved in verifying them. On-premise audits focus on evaluating the security of systems housed within the organization's own physical data centers and infrastructure.
Checking your own gear.
Right. The audit will examine physical access controls, environmental controls like fire suppression, cooling, network devices, servers, applications, everything within your direct control. Auditors might physically inspect data centers, review logs from internal systems, verify configurations on hardware you own. Cloud audits, in contrast, assess the security of data and applications hosted by cloud service providers. This requires that nuanced understanding of the shared responsibility model we talked about.
Shared responsibility again.
Always in the cloud. Auditors need to know which controls are the cloud provider's responsibility versus the organization's. They'll focus on the organization's configurations within the cloud environment, things like identity and access management, IAM, network security groups, data encryption settings, and they'll review reports provided by the cloud provider, like their SOC2 report, to gain assurance on the underlying infrastructure security. And hybrid audits examine the security measures and connectivity between an organization's on-premise resources and its cloud environments.
The connection points.
Exactly. This type of audit specifically focuses on the interfaces, the data flows, and the security controls that bridge these two distinct operational locations. For example, how is data securely transmitted between an on-prem database and a cloud application? How is identity federated across both? It ensures a consistent and robust security posture across the entire distributed infrastructure. Each scenario demands specific considerations in the audit approach and often specialized expertise from the auditors.
This raises an important, overarching question that ties all this together. All this discussion about assessment, testing, and auditing seems like a continuous cycle. How does an organization truly ensure it's maintaining its security posture over time, rather than just doing a series of one-off checks that quickly become outdated? How do you make it stick?
That's precisely the point, and it's really the ultimate takeaway for this domain. It's about recognizing security assessment and testing not as a project, but as an ongoing, adaptive, and inherently continuous process.
A process, not a project.
Exactly. It is absolutely not a one-time check or a simple checklist to be completed and then forgotten until the next audit cycle rolls around. Instead, it represents a fundamental commitment to continuous vigilance, relentless improvement, and proactive adaptation. The goal for any mature organization is to embed these practices, security assessment, control testing, rigorous auditing, so deeply into the organizational culture and daily operations that they become a natural, inherent part of how systems are designed, built, deployed, maintained, and eventually decommissioned.
Making it part of the DNA.
You can say that. Integrating security into the entire life cycle of every asset, from concept to end of life. By doing so, an organization transitions from being merely reactive, only responding to incidents after they occur, to being genuinely proactive, identifying and mitigating weaknesses before they can be exploited.
Proactive versus reactive.
Right. It requires always learning from past assessments, adapting to new threats as they emerge, leveraging new technologies for testing and defense, and constantly seeking to strengthen defenses against an ever-evolving threat landscape. It truly is a never-ending journey of continuous improvement, where the insights and findings from one round of assessments feed directly into the planning and execution of the next, ensuring an organization's security posture is always evolving. That brings us to the end of our comprehensive exploration of CISSP Domain 6, Security Assessment and Testing. It's abundantly clear that understanding how to design, conduct, and analyze security tests and audits isn't just theoretical knowledge. It's absolutely fundamental for any security professional looking to build and maintain truly robust, resilient, and defensible systems.
Thank you for joining us on this discussion. Don't forget to like and subscribe, and don't forget to check out our CISSP playlist for more insights into all the domains.